Hey everybody, Corey and Victoria here. We are the Professor's Du Bois, and we're going to do a thermochemistry unit, and specifically in this lecture we're going to talk about energy and specific heat.
Well, what the heck is that? So chemists are interested in why things happen, and we use thermodynamics to help us answer that. So there's a thermodynamics piece and there's a kinetics piece. So there's kind of like a why does it happen, what will happen spontaneously, and what won't, and then there's how fast it will occur. And we're going to get into kinetics in the second semester of general chemistry, and we're going to work on thermodynamics and in particular, like the energy or the heat or the change in heat for chemical reactions. So
far we've talked about mass, and we've done some stoichiometry with mass, with chemical reactions, but what we haven't talked about yet is that there's actually an energy component in a chemical reaction. And the energy could either be given off as like heat energy, and this would be called an exothermic reaction, or it could be an endothermic reaction, which requires energy. So in this chapter, when we're talking about energy, we're really talking about heat. And we're talking about heat in reactions and the transfer of heat in matter.
That's true. So energy, what is energy? We have kinetic energy. You've probably heard of kinetic energy, and that's the energy of motion. And we as chemists think about the motion of the atomic scale, so the energy and the movement of the molecule. So within a solid, it's vibrating, and within a liquid, it can translate and move and rotate. And this is all kinetic energy. And you can calculate the kinetic energy with 1/2 mass times the velocity squared. Now, potential energy is the energy that's stored in a body, and it's based on its position. The total energy is both of those added together, and just like mass, it can be neither created nor destroyed. So we have a conservation of mass and a conservation of energy.
The unit we're going to use for energy is the joule, and it's going to take a little getting used to. Like, we know when we see grams, we know that that's a mass unit, and I think it's a little tricky at first because we haven't worked with this unit very much. To realize that that's the energy. So it's just something to know that we're using joule. It might be kilojoules, but that's the unit we're going to use. It's not the only unit for energy. There's an older energy unit. It's the calorie, and the calorie was defined by the amount of heat required to raise the temperature of 1 gram of water 1 degree C. Now this calorie was written with a lowercase c. The food label calories are written with a capital C, which is actually 1,000 of those lowercase c's.
Hey, tricky.
And so it's really, the food label is really in kilocalories.
Right.
There are, conversions between these units. For instance, 1 calorie is equal to 4.184 joules. You may have to do some conversions. These conversion factors will be provided.
So more definitions. We have to define our system, what we're worried about, what we're thinking about, what we're trying to calculate and find something out about, versus surroundings. And with energy, we're concerned about, okay, where is it coming from? Where is it going to? And what's happening when the energy gets there? So we have to define, okay, what are we talking about? Is energy leaving that system, or is it entering the system? And anything outside of the system or the reaction or change that you're concerned with is the surroundings. So everything else in the whole universe is considered the surroundings. So we have this conservation of energy. Any energy that was given off by the system will be gained by the surroundings, and vice versa.
So defining the system and surroundings can tell us if a reaction is endothermic or exothermic. So our system is usually what's going on inside the flask, and we've got a nice pair of Erlenmeyer flasks here drawn to scale and perfection.
Yeah.
And on the left we have you can see heat is leaving, it's exiting this flask. So the flask is actually part of the surroundings. So the flask is getting hot, and there's heat going out into the air and into the atmosphere. This is an exothermic reaction going on inside this flask. On the right-hand side, we can see the heat direction is going into the flask or into the system. So that this particular reaction is endothermic. It requires energy, or it takes energy from the surroundings in order to happen. That's an endothermic reaction.
Energy is entering for endo, energy is exiting for exothermic. Okay, temperature. We're all familiar with temperature. But do you know that it's defined as the measure of average kinetic energy? So this is measuring how much motion is going on in your system or surroundings, whatever you're measuring. But energy flows from the hotter object to the colder object. So we like to say heat flow from high to low until thermal equilibrium is reached. And thermal equilibrium is when the temperatures are the same. So as long as the temperatures are different, heat will flow until it's the same. And heating and cooling are processes by which energy is transferred as heat from an object. Heat's not a substance, heat is energy, and it's not temperature. Temperature is the measure of average kinetic energy. And we also are entering here, we have a new unit, and we're calling that Q, and Q is heat.
So when an object is heated or cooled, the quantity of energy transferred depends on three things. Now, the quantity of material makes perfect sense. It's going to take more energy to heat or increase the temperature of a larger quantity of material than a smaller quantity. So quantity, of course, will matter. The other thing that's really obvious is the size of the temperature change. It's going to require more energy to have a bigger temperature change. The one that's not as obvious is that material gaining or losing the energy has an intrinsic property, meaning we can use this to maybe identify the property because it's unique to that material, and it's called specific heat capacity. Now, if you look at the units, we've got a few examples here. The units are joule per gram Kelvin. Now, it could be joule per mole, it could be kilojoule per mole. Those are all, we can get there from joule per gram. And the Kelvin is often written as Celsius, and we're going to talk about that in just a second. But what this is saying is that water requires 4.184 joules to raise the temperature of 1 gram, 1 degree Kelvin. Now, gold only requires 0.129 joules. So if we put a burner on some water and some gold of the same mass, the gold's going to get hot much, much quicker because it only takes 0.129 joules to raise the temperature of 1 gram, 1 degree Kelvin. Another thing worth mentioning is that the three gold, copper, and aluminum are metals, and metals have pretty low specific heat capacities. And usually, I think they're usually less than 1. There might be some metals that are right around 1, but you're not going to see any of the metals up there at 4. That's pretty high. So, just some food for thought. If you're calculating a specific heat capacity for a metal and you get a number in the millions, you made a mistake.
Yeah, and water, the high, can you go back for a second? The large heat capacity for water is really important for biological systems and for just really our climate. So if you think of water, the oceans or a large lake, how it affects climate, it's because it's resisting the change in temperature. So it takes a lot of energy to change that water's temperature, and then once the temperature has changed, it takes a lot to then change it back. So it takes a lot of energy to heat that water up, but then it also takes a lot of energy to be removed in order to cool it down, and that plays a big part in our climate.
And you think about this, and I know we don't have a ton of time, but climatologists are very concerned about temperature changes in oceans of like a degree, and you're like, well, 1 degree, what a big, that's not a big deal. Well, look at the mass of an ocean, like the mass of water, and look at the energy that would have to be involved. If it takes 4 joules to raise 1 gram, 1 degree, I mean, think about raising the temperature of the ocean 1 degree. It's a tremendous amount of energy.
Yeah, good point. All right, Kelvin and Celsius relationship. Kelvin is Celsius plus 273, so it's just an additive number, so it's just offset by 273 degrees. But 1 degree change is the same for both, and you can see that here. If we subtract these two numbers here, we get 3 degrees Kelvin change. We actually don't use the degree symbol for Kelvin. And if we subtract these, we get 3 degrees Celsius. And the difference between 1 degree, the magnitude of 1 degree is the same for Kelvin and Celsius. So if you have a delta T, if you have a change in temperature, T final minus T initial, whether it's in Kelvin or whether it's in Celsius, it's the same number. So a delta T, it doesn't matter if you use Kelvin or Celsius as long as it's a change in temperature. It's not an absolute.
You took my slide.
I did.
So we can measure the energy gained or lost as heat when a given mass is warmed or cooled using this formula. Q, that's our heat, is equal to the mass times the specific heat capacity, noted with a C, times the change in temperature. And that delta, it looks like a triangle. Delta T just means change in temperature, and that's the final temperature minus the initial temperature. And the sign of this value, it could be positive or negative, and that's going to indicate the direction of heat flow. And we're going to show an example of how that indicates heat flow.
Okay, here's an example that you might see. The specific heat capacity of copper is 0.385. Makes sense. It's a metal, should be small. What's the energy change? Okay, so what is the energy means we're looking for Q.
Units?
Joules. If we have a mass of copper and we have a change in temperature. So we're solving for Q. We're provided the mass, we're provided the specific heat, and remember that the delta T is the T final minus the T initial.
So we've got one object, we've got a mass, a specific heat capacity, a delta T, and we end up with a value of 2450 joules, or they might have asked for it in kilojoules. We can convert that. So if we're heating, we're adding energy to the copper. That's endothermic. Energy's going in. We have a positive Q. That's going to be endothermic.
Positive means endo. That's really important. Energy entering in order to increase the temperature. All right, so here's a practice problem. Give this a try. Pause the video, and we'll see how you do.
Now, I want to just talk about it a little bit because it says it's heated for 2 seconds. And it says that 100 joules of heat energy is transferred. Now, it didn't say 100 joules per second. It gave us the total joules. Joules, that's Q. So that 2 seconds, just a distraction in there. Don't worry about that. And our final temperature is 71.9, if you're a little confused on that. And we've got a mass. You're going to calculate specific heat. It told you it was a metal. I would expect a value less than 1.
There's your answer.
I don't know why the writing keeps coming on the next slide, but it's
sorry about that.
It's a little distracting. The answer 0.385 units. Make sure you always include those units. Joule per gram degrees C. Maybe you converted this to kilojoules, and that's okay too. So that's what we have for you.
Thanks for watching. We appreciate it. That was the intro to thermochemistry. Come back for more.